Good evening, everyone. We are Group 3, and this is our DSA course project presentation. Our topic is Ternary and Exponential Search. So, let's move on to the introduction. Of course, we all know about the searching algorithms. We all know the classics, linear search and binary search. As in the name, linear search has this time complexity of linear time, and of course, binary search is probably the most famous search out there. You all know what it does. Some other notable searching algorithms can be Fibonacci and term search, multiplicative binary search, and meta binary search. But the two that we will focus on today are ternary search and exponential search. So, what is ternary search? The concept is quite simple. So, for binary search, we split the searching range into two. So now, as the name suggests, we split the range into three. There are two variants here: discrete ternary search and continuous ternary search. Um, yeah, so the script is basically like binary search. We search in a sorted array to make it simple. So yeah, but for continuous, it's a little bit different, and it's something that binary search cannot do. Is that we find a single extremum on a unimodal function. What exactly is a unimodal function? We will talk about that later. Now, discrete ternary search. So again, how we implement it is extremely similar to binary search, but just a little bit more complicated. We calculate the two midpoints and we compare them to the target value and update the searching rank accordingly. And yeah, we just keep repeating the process until we find the target, or unless the left index is larger than the right index. When when that time comes and the target is still not found, we return a value, maybe -1. And this is how we can implement it. Again, the idea is very similar to binary search. And the first one was the iterative version, and this one is the recursive version. We don't exactly recommend using this, but it's here for those who are interested. Now, let's have a quick visualization of the algorithm. Here, given this array, we're trying to find the value 34, right? So for the so before the first iteration, we need to calculate the two midpoints first, and you can see them green and red on the screen. And for the first iteration, we find out that the value at index mid 2 is smaller than our target value, so we update the searching range accordingly. And we do it one more time, and at the second iteration, we found the value at index mid 1, the yellow. Yes, yes. Now let's calculate the time complexity of the algorithm. At each iteration, two values is calculated, like I said before, and two-thirds of the search range is decreased in each iteration. So after the first iteration, search range is become a third of n, and for each iteration, it reduced by one third. So obviously, we can imagine that the time complexity is logarithmic time. For the best case is instant that either the midpoint value is the target, and that is the worst case. The auxiliary space for the iterative version is constant. We don't need any more space, only for the midpoints variables. But yeah, those are negligible. And but for the recursive version, we need to call stacks, and that's why it's logarithmic. So for the discrete ternary search, one question arises: why don't we use it if the allegedly the time complexity is better, right? The time complexity is better here. But if we really dive down deep, ternary search isn't more effective than binary search. And obviously, the array that we search on needs to be sorted because the algorithm is based solely on the comparisons of the two midpoints and to the target. If the array is not sorted, there's no way that the algorithm can run correctly. Now let's move on to the second version of ternary search, continuous ternary search. Like I said before, we now will define what is a unimodal function. So simply is a function that increases, then decreases, then increases and vice versa. So here we have two graphs that show what I just said. This is the statement problem. It explains the exact same thing. So, what is the concept here? Similar to discrete Ternary search, we also calculate the two midpoints, mid one and mid two. But now we also compare it to the not exactly to the target value because there are no target value here. We have no idea what we are looking for. We only know that it's either the biggest one or the smallest one. Let's assume it's the big one, for example, but we compare the two values of the mid one and mid two together, right? And we have three cases here. The third case is most of the time is negligible. We don't care about that. And for the first and second case, we can infer that it's either a downward trend or upward trend. And after that, we can say that oh, it either lies in the leftmost part. No, no, not exactly leftmost part. The left two parts of the search range or the right two parts of the search range. So this is how we implement it. As you can imagine, at every iteration, the search range is decreased by one third. And this is the visualization that we come up. Um, the search function, the function is there. This is an array. This is a function that increase then decrease, and we're looking for the maximum, right? So first we start at the left index and the right index at 10, and then we iteratively decrease the search range by one third. So this version of the algorithm that we have here took 41 iterations to find an acceptable point that we just stop the algorithm there. Yep, this is how we calculate the time complexity. It's different than the discrete Ternary search, right? Because the average, the search range is only decreased by one third each iteration. But the time complexity in general is the same. The best case and the worst case is also the same. So it's a little bit different because again, we're not looking for exact value here, but we are actually looking for an estimation, right? So assume very large values for the left index and the right index. After 100 iterations, the interval range reduced to a very, very small value, and we can consider that sufficiently precise. Yep. So the next part will be the applications and the improvements of ternary search.
So let's now move on to application of tail research. Tail research is widely used in optimization problems involving a function with a single extremum, especially in competitive programming. Let's go through a sample problem. Dang is student who needs to earn money by selling n buns. He has two options. He can sell the first k buns at decreasing prices, starting from b down to 1. The remaining n minus k buns are sold at a fixed price A. The question is, what is the best value of k that maximizes down total profit? From this problem, we can define the profit function as follows. This function is quadratic with the single maximum point means it's unimodal. Therefore, we can directly apply tail research to find this maximum point, which represents the maximum amount of money that can earn. So we move to the improvement of tail research. Next. Okay. Moving on to the algorithm improvements, we will now go through two key observations that help us optimize research in practice. Observation one, in tail research, we always discard one of the outer thirds, but the middle third is always kept. This means the smaller the middle segment, the more we eliminate in each step. So, a natural question arises. How should we divide the interval to eliminate more? It turns out that if the two division points are placed closer together, almost merging, then the middle segment becomes very small. As a result, we discard more at each step, and the algorithm approaches the behavior of bar research, reducing complexity to log to n. And here's the code. The using this division, we the number of iterations become fewer, and the complexity tends toward O log to n. And so the observation too. Now let's consider: can we reduce the number of times we evaluate the function fx? It leads to the natural ideas of reusing a previously computed point. For example, we can reuse f mid 1 or f mid 2 from the previous iteration instead of recalculating both. However, if we kept the standard 1:1 ratio and reuse point, we end up with unbalanced divisions where one side becomes significantly larger than the other. It leads to instability in algorithm. To maintain balance with reducing point, we turn to special mathematical ratio, the golden ratio, and is the demonstrate. Through mathematical derivation, we find that dividing the interval based on the golden ratio preserves balance and allows point reuse. This results in the well-known golden ratio search algorithm. So let's now compare the two optimized approaches in terms of performance. In the improvement one, we can calculate the time complexity. Uh, no, next, next, next. Yes, this is the time complexity of the Ternary search, and this is the time complexity of a golden section search. Based on this formula, we analyze if the function fx is fast to compute, then improvement one performs better. If fx is slow or expensive to compute, then GSS is the better choice since it makes fewer function calls. However, it's important to note that both approaches still have logarithmic complexity, and for most real-world problems, either one will perform sufficiently well.
And now I'm gonna present about the exponential search. Exponential search proposed by Andrew Chi Yao and John Bentley in 1976. It has many different implementations. Most common one is determining the search range then performing binary search. Now we come up with the proposed algorithms. From now on, let's call the list to be searched R and the desired value key and its corresponding index M. The cost of computing a certain algorithm B we will define by CB of M. Algorithm B0 or linear search. The most straightforward algorithm for unbounded searching is to test every value R0, R1, R2 until Rm is equal to key. It is easy to see that the cost of the algorithm is M. Algorithm B1 or exponential search. In step 1, we determine the range that the key might reside in. We achieve this by doubling the temporary bound of the search range until the value at the boundary index is greater than key. If the desired value is in the list, it has to be in the range as follows. This action takes log m plus 1. And in step 2, we perform binary search on the found range. This action takes total step of log m minus 1. Conclusion, the algorithm B1 achieves time complexity of log m. Let's talk about the sorted criteria. Exponential search is designed for sorted lists because it leverages the order of element to efficiently narrow down the search range and perform binary search. On unsorted arrays, this approach fails because the necessary order is missing. Consider an unsorted list as follows. If you try to use exponential search to find a value for, the doubling boundary strategy will not help in identifying a meaningful range. Even if a range is identified, binary search will not work in that range. Algorithm B2. This algorithm improves the first step of algorithm B1 by, instead of doubling the boundary, we now raise it to the power of 2 for every boundary size larger or equal than 2. It should then be as the expression as follows. Conclusion, the algorithm optimizes the complexity of V1 from 2 log m to log of log m plus 1 plus log m minus 1. Algorithm BK. And now we extend from algorithm B2, instead of just raise the to the power of 2 once, we now raise it k times. And now this is the spirit of the progression algorithm proposed by Andrew and John. To analyze algorithm BK, we define a function Lj of m recursively as follows. And we define another function Lj of m. Then proving by induction, we have the following equation, where Lk of m plus 1 represent the cost of finding the boundary in algorithm BK, and the cost of corresponding binary search is 2Lk plus 1 of m plus 1. We now have an infinite number of unbounded searching algorithms, B0, B1, B2, which one should be chosen for a particular search. As for algorithm U, the first stage we choose an appropriate K, and the second stage we then use algorithm BK to solve the problem. We propose to choose K that follows the following rules. And by the definition of the function Lj of m, we can see that L star of m is the minimum j such that Gj greater or equal than m, where G is defined recursively as follows. And the total cost of algorithm U is right as the following equation. Now let's go to the implementation of the algorithm. We will focus on the implementation of algorithm B1, as this is the most common implementation proposed by the author. For example, let's choose array R with 20 elements and the desired value key equal 19. In the first stage, we find the boundary. We start with an bound index R equal 1, and we keep doubling it until we find a valid index that satisfies R of R that's larger than key. In this situation is 16, and then we exit the stage. In stage 2, we use binary search on the found range. This is the visualization of the proposed algorithm. Let's analyze a bit about the implementation. In the best case, the key value is at first position of the list, so it returns and exit the search immediately in constant time. In the worst case, the key value is at last position or larger than last element, which takes all of log m, like binary search. And in the average case, is anywhere else on the list, which takes all log m, where m is the index of the key. Let's compare it to binary search. Exponential search is faster when the key is near the beginning of the list. The algorithm can quickly narrow down the search range, making it faster than binary search. Example: consider a list of size n equal 1024. If the key is at position I equals 16, in exponential search it takes 08 time complexity, but binary search takes 010. The table below shows the total running time of binary search and exponential search when searching for 5 different keys on the same list R of size n. Despite having the better overall time complexity than binary search, our exponential search runs significantly slower. What's the reason behind this? Let's reconsider the average time complexity. In case 1, the index of key is on the lower half of the array, and in total, both the operation takes log n over 2 minus 1, so the total of log n minus 2 computing complexity. But in case 2, where the index of key resides on the upper half of the list, each operation takes at least log n over 2 basic operations, and in total, the search achieves log n computing complexity minimum. To sum up, when the index of key exists on the upper half of the list, exponential search performs worse than binary search. Thus, on the average case, exponential search gives up the same time complexity as binary search. But then we have to come up to the practical considerations. The constant factors and overheads, where exponential search involves additional operations, which can introduce more overhead compared to the simpler binary search. And along with the cache efficiency, binary search access element in a more predictable manner, leading to better cache performance. Conclusion: exponential search performs worse than binary search when searching for a desired value on a sorted bounded list. We have come up with a variation of exponential search. The idea is to recursively call the exponentiating function to adjust to a new range resides in the previous found range until it only contains one element left. By removing the need of binary search, this method is far superior. Furthermore, it can also be used for searching on unbounded lists. From the nature of the variation, we call it dynamic exponential search. In step 1, we initialize the searching range. In step 2, we call exponential search function with range as well. And then we perform finding a new boundary by finding the minimum j such that it satisfies the condition. In step 4, we update the range to the newly found range. At step 5, if the new range contains only one element, or L is equal to R, then return else at the found index, else return to step 2. Here is the pseudocode of the dynamic exponential search, both recursive version and the iterative version. Now let's trace the algorithm. We now use a 20 elements list and a preferred key equal 27 so can fully graph the searching process. In the first recursion call, we have an index L and a temporary variable I. And we keep doubling the variable I until L plus I equals such an index that satisfies the value is larger than key, and we call the next recursion. In the second recursion call, we do the same thing. We can see now it runs faster than the first recursion as the range is narrowing. In the third recursion call, we do the same thing. In the fourth recursion call, we found that the first element of the range is equal to key, and then we return the index. This is a visualization of our proposed algorithm. And this is the table that shows the running time of our proposed algorithm comparing to binary search and the author's exponential search. And from observation and measuring, the dynamic exponential search performs worse than binary search and exponential search on lists of length lower or equal than 400,000 at around and over a half a million. The iterative version of the algorithm excels in performance, surpassing other searching algorithms. To analyze the complexity of the code, we call the algorithm BA, and we reuse the predefined function L from algorithm BK. From the recursion calls, we can prove that the cost is a sum of Lj of m, where j is from 1 to k, where k is the final recursion call, which Lk of m is equal to 1. And we also have L1 of m is far greater than L2 of n, and so on. Therefore, for every m large enough, the cost of algorithm BA is approximately L1 of m, which is log m. In unbounded lists, we do not have an initial boundary to use binary search. This is where exponential search come in the clutch. Exponential search can perform finding the boundary, which also double up as the key searching function. In fact, exponential search does not even have to find the actual boundary of the list. It can terminate the boundary finding stage when we found a range that the key would likely reside in. Exponential search can be used as a variation to solve the global pairwise alignment problem, which involves aligning two sequences such as DNA, RNA, or protein sequences. Let's talk about a problem. Exponential search can be used to optimize certain aspects of the alignment process using a method called band doubling. Particularly when dealing with large sequences, here's how it works. Basic concept of band doubling. In traditional band alignment algorithm, we fill an entire dynamic programming matrix of size m times n, where the variable are the lengths of the sequences. This has O m times n time and space complexity, which comes prohibitive for very long sequences. And this is the algorithm. We start by the initial band with a narrow band of width k around the main diagonal of the matrix. In the first pass, we compute alignment score only for cells within this band. Then we check alignment, determine if the optimal alignment falls within the band by checking if the score at cell MN can be reached without going outside the band, and we double if needed. If the optimal alignment might lie outside the current band, detected by binary cells having better score than expected, double the band and repeat. We will terminate the function if it reached the optimal alignment is confirmed to lie within the band or if the band covers the entire matrix. And this is visualization of the band doubling method on two sequences of length 32. The advantages: reduce complexity. For similar sequences, this can reduce the time complexity from O of m times n to O of m plus n plus d to the power of 2, where d is the edit distance between sequences. And the memory efficiency, since we only store the current band, space complexity is reduced. The method adapts to the similarity level of the sequences. Very similar sequences will complete with narrow bands, while the similar ones might require wider bands. Application in practice. The band doubling approach is particularly useful for aligning extremely long sequences like chromosomes. Initial rapid alignment before applying more precise but computationally expensive methods. In scenarios where sequences are expected to be relatively similar with limited insertions, deletions. This method represents one of the several heuristic approaches, along with techniques like diagonal bands, I-star search, and seed-based methods, that makes sequence alignment practical for large biological sequences.
And that is our presentation. Thank you for your attention.